First of all, I appreciate APT for this initiative, and I'm pretty glad that we have chosen to conduct a series of workshops in theoretical physics, and I'm very glad I am chosen to initiate this workshop. So I thank Hari for a nice introduction, and thank also Dr. Satya for taking initiative to invite me and start this series, first workshop of it. So the plan is something like this. There will be 2 lectures for this session. We will have tutorials in the afternoon session, and we will do some problems. So only thing you are all teachers, and you know, and some of you may be more experienced than what I am. You know that attending a lecture does not teach us anything. Only hands-on experience will make us know that whether we have understood something or not. So that is the reason why I think very nicely this course is planned in such a way that half of lectures and half of lectures. So we will be talking in these 2 days complex variables. So the first lecture I intend to cover complex numbers, functions of complex variables, analytic functions, then Cauchy integral theorem, Cauchy integral formula, and Taylor series. So let us start with complex numbers. Complex numbers came into existence for there was a requirement that if you have an equation like this, x square plus 1 is equal to 8. We do not have any solution for this equation in the real life. You cannot find an x in the real life that satisfies this equation. So, no real x exists. That satisfies above equation. So you define that as a, so define I such that I square equal to -1. So the solution is I. We define an I square is equal to -1, and this is not a part of the real life. So any complex number requires 2 real numbers. We call them an ordered pair of real numbers, x, y. We represent it in the following fashion: z is equal to x plus I y, because there is coefficient of one real line coefficient of I is another real line. So you have one real line and another real line, and x and y, they don't depend on each other. So they are independent real numbers. So two independent real numbers are required to define a complex. Then you can write it as an ordered pair like this, or you can write it in this fashion. So, since you require two independent real lines that constitute a plane, so this is what is called a complex plane. Complex plane which is denoted in this fashion, where this is x-axis is the real line, y-axis is I times the real line. So any arbitrary point in the complex plane can be written as z, which is equal to x plus I1. So this is the real part, and this is imaginary. So we say the real part of z is equal to x, imaginary part of z is equal to y. So real and imaginary parts of a complex number are real numbers. Okay. Now, since I have put this as a complex plane, I can always consider this particular notation, where this is magnitude, which I will call it as r, and this is the angle from the real axis, which I will call it as theta. Then I can write down real part of, you can write this as r cos theta, and this you can write it as r sin theta. As a result, the complex number z is written as r e power I. This is called polar representation. This is called polar representation. Okay, so for this, you can immediately see that it can be shown that e power I theta is equal to cos theta plus I sin theta. Then only you can write it like this. This is r cos theta plus r sin theta. Pull out r equal to cos theta plus I sin theta, which I have written as before, right? Okay, the proof is very simple. If you know that, so I will not prove it, and I will prove proceeds by expanding e power I theta as sum over j is equal to 0 to infinity I theta power j divided by factorial. This is e power x expansion, and you expand and then separate terms that have I and separate terms that don't have I. Then one series will give you cos theta, the other series will give you sin. So I will leave this for you to work out, and if you have some difficulty in the tutorial, you can come back. Further, you can also show that e power I n theta. It doesn't matter whether theta is there or n theta is there. This n theta I can call it as phi, and then I will use the same. It is nothing but cos n theta plus I sin n. This is a useful expression which we can make use of solving some problems. Okay. Now, this is in some sense what complex numbers are. Now, the question that we can ask is that when we had x square plus 1 is equal to 0, the real numbers that we were having at our disposal are not helping us to find a solution in them. Then we had to define I square equal to minus 1 and then attach another real axis or the complex plane, and then we have solutions to this kind of equation. Now you ask a question, suppose if I have, so ask this question, what is the solution of x cubed plus 1 is equal to 0? Do I have to define another quantity such that some j cube is equal to minus 1 or something like that? Are solutions, is complex plane enough to find solutions of such equations? It turns out that you can find solutions of this equation in the complex plane. Okay, so complex plane, you don't require anything more than this. Number system is closed. You start with natural numbers, you required integers, that is negative numbers, then you had equations like 2x plus 1 is equal to 0, then you required rational numbers, then you had a requirement for irrational numbers, right? So you had this kind of, for example, 2x minus 1 is equal to 0, needed rational numbers. And x squared minus 2 is equal to 0 required irrational numbers. And equation like this require complex numbers. And you may, going by this sequence of requirements, you may think that x cube plus 1 may require some more numbers, but the number system comes to close. So all algebraic equations, x cube, x power 5, whatever algebraic equations that you can write, their solutions are the roots will all lie. Okay, so complex plane which I denote it with this accent contains solutions of all algebraic we can perhaps find out what those solutions are. If, for example, this equation, this implies x cubed is equal to minus 1. So you have to ask the question, definitely there may not be real roots here, only we don't have a real roots even for x square is equal to minus 1. So x cubed is equal to minus 1 requires some complex numbers. Okay, so since we have a plane since we have a plane, so remember when we had real numbers, this is a real line extending from minus infinity to plus infinity. We call as real. So you have two directions in which a variable can go to infinity. Okay? It can go to plus infinity or it can go to minus infinity. Now when you come to complex plane, if I say there is a possibility that I can go to plus infinity, minus infinity along the real or along imaginary or along any other directions, there are so many infinities. There are infinite ways in which you can go to infinity. Correct? This notion is important because when we define a real variable and then we define calculus, for example, I want to ask a question: what is the limit of a function of a real variable? Then you know that if you have a function of a, so let's say consider the function of a real variable. Let's say this is x, and I have some function f of x. So this is, let's say, f of x. Then I want to find out what is the limit of this function at x naught. And what is that we do? We take x approaching x naught from this direction and x approaching x naught in this direction. So we calculate limit of f of x as extending to, we write it as x naught plus, that means coming from plus direction, should be equal to limit f of x as extending to x naught minus, and they both should be equal. Then only we say that the limit exists. Correct? So we should go from this way, we should have the same limit, then we say that the limit exists. Then limit extending to x naught, f of x naught, f of x exists. F of x naught itself may not be existing. It is possible that f at x naught has no value. But if this limit from left and right exists, the limit exists. If you want to understand same thing here, you have some function and you have some z naught here, then you must imagine that you must be able to come to this point in any direction. There are infinitely many directions in which you can come. All possible directions, when you take the limit, you should get the same value. So you can see there's a stringent requirement here. It's not just two directions, but there are infinitely many directions. And you should get the same limit. So you have to write it in this fashion, that limit f of z mod z minus z naught tending to 0. When I say mod z minus z naught, I don't care which direction. It is like we are shrinking this circle. Okay. And then is the limit. Should be same. Okay. Similarly, continue. If you say you have a function f which is continuous at some point, limit should exist, but the existing limit should be also same as the value of the function. So this real, just like real number system goes from minus infinity to plus infinity, complex plane will also go to infinity and infinities in all possible directions. And if you want to define the distance between 2 points, you know, you cannot order points to plane unless you define an appropriate norm of the distance. So if I have 2 complex numbers, I must define. So if I say I have a z1 here and a z2 here, the distance between these 2 points is nothing but modulus of z1 minus. How to define this one? For that we must define what is called a complex conjugate. So if we have a complex number, so if z is a complex number x plus iy, then we define its conjugate, that star is represented as, which is x minus y. So this is called complex conjugate. Complex conjugate. Now complex conjugate, and you can write down z star as mod z square. This is a real quantity which actually you can write it into x square plus y. So a distance or a magnitude function can be defined as mod z is equal to square root of z into z. So this modulus is what I am using to define the distance. Z1 minus Z2 is, so you can immediately, so we can show that for any Z1 and Z2, in the complex plane, mod Z1 minus mod Z2 is less than or equal to Z1 plus Z2 is less than or equal to mod Z1. We take this much, this is called triangle inequality, which is required for any function to be qualified as a distance function. Now, okay, let me just give a quick proof for this. The proof is, just consider, you can prove things in many ways. So usually proofs and problems, when I solve, they are the way I think is correct, but there is no unique way of solving. You can solve in a different way. Usually that is why in teacher training we were generally asked not to solve problems in the class. Why? Because everybody will learn the way I solve. But we have to keep individual differences alive. So we must allow people to solve, so that each one will solve in their own way. And some may be solving in a elaborate mathematics may be used, some may be with a useful trick. So I think we generally try to discourage people to follow the way that I am proving, and you can prove in any other way. So I will give one proof. So I will say that Z1 is equal to R1 e power I into 1, and Z2 is equal to R2 e power I into 2. So Z1 plus Z2 modulus is given by square root of R1 e power I theta 1 plus R2 e power I theta 2. This is Z1 plus Z2 into R1 e power minus I theta 1 plus R2 e power minus I theta 2. This is Z1 plus Z2. This is conjugate of Z1 plus Z2. So that will give you square root of R1 square plus R2 square plus, I will write down directly 2 cosine of theta 1 minus. This is what I will get if I take it. Now you can see that this cos will vary between minus 1 and plus 1. The minimum value of this cos argument is minus 1 and maximum is plus 1. So if cos of theta 1 minus theta 2 is equal to minus 1, then this is the minimum value. The minimum value. Then we have Z1 plus Z2 modulus is equal to R1 minus R2, which is same as mod Z1 minus 1. This is the minimum value that is here. And if cos theta 1 minus theta 2 is equal to plus 1, that is the maximum value. Maximum value, then Z1 plus Z2 modulus is equal to R1 plus R2, which is equal to mod Z1 plus mod Z. This is the maximum value that we take, which is the statement of this. So the maximum, minimum and maximum is equal like this. Okay, so we have learned about complex numbers. Okay, so having learned about complex numbers, see, whatever I have done so far in this section is nothing new, right? You all might have known this and you all might have taught this several times in your colleges. But when we are trying to use whatever we have learned, we are trying to use, we should know whether we are able to use. Okay, so that can be done only when we are solving some problem. For example, if I say find real and imaginary parts of the complex number z, which I will define as I to the power root I. Suppose I ask something like this. So we know how to define complex numbers. We know what is I, we know what is everything we know. But can we quickly find what are the real and imaginary powers of this? I raised to the power square root of I. Anyone has any clue? Normally, in problem solving strategies, if we are confronted with a problem which is very difficult to solve, what we do is we try to ask simpler questions, and the limit point of those questions will be this problem. Okay, so we don't know how to solve this problem, that's fine. But then can we ask a simpler question which can be solved? And get an experience, the sum total of the experience should help us to solve this problem. Like for example, if I say I to the power some real I to the power, let's say some n is some integer, let's say. So is it real, or what are the real parts of that? Can we say that I to the power n, is it real? Depends on n, right? Unless I say what n is, you cannot say that is real. So if n, so this is equal to, generally what you can say, if n is equal to 0, it is 1. If n is equal to 1, it is I. If n is equal to 2, it is minus 1. If n is equal to 3, it is minus 3. So it will be between 1, I, minus I and minus 1. So I power n will be one of these four values depending on n. So I power n will belong to this This is also true if n is negative also, right? 1 by I is minus n, 1 by I square is minus 1, and so on. So for all integer values, I power n will belong. What about, so there is no problem. What about I power half? Because we require, this quantity is there here. So if you understand what is I power half, then you will understand how to use it. What about I power half? What is square root of I? We have to think all possible things that we know. I am not asking anything that you know before, but whatever we discussed in today's morning is sufficient to answer all these questions. So what we can do to answer this question is, we know that every complex number is written in the polar form. So I will write this in the polar form. What will be I in the polar form? I is equal to cos pi by 2. Cos pi by 2 is 0. Plus I sin pi by 2. Sin pi by 2 is 1. Correct? I think I did not write that equation, that if you have z is equal to x plus iy, and if you want to write this as r into e power I theta, r is related to x and y in this fashion, x square plus y square, theta is related to tan inverse y by x. From this picture, it is clear, right? So tan inverse y by x. So if I use that, this becomes 1. R becomes 1, and this becomes tan inverse 1 by 0. Tan inverse infinity is pi. It could be minus pi by 2 also. Pi by 2 is 1. So you can write this I power half or square root of I as e to the power I pi by 2. E to the power I pi by 2 is I to the power half. So which is equal to e to the power I pi by 4. E to the power I pi by 4. What is that equal to? cos pi by 4 plus I sin pi by 4, and cos pi by 4 and sin pi by 4 are 1 by root 2. So this is 1 plus I divided by root 2. This I to the power half. So in general, we have I to the power n integer, I power half, rational number, or in general if you ask what is I power p by q, a general rational number, this is nothing but p power I e I, and depending on what is q and p, okay, so you have to keep this q not equal to 0 here. So a rational number